We figured out the total temperature and total pressure coming out of the compressor. We're ready to move on to the combustor. And so the combustor is a little bit of a different beast in that we already know the outlet total temperature, and we have a pretty easy way to calculate the outlet total pressure. So our real challenge here is going to be determining the mass flow rate of fuel that's required to achieve these changes in temperature. So we'll start off with the total pressure. We know that the burner pressure ratio, pi b, is equal to PT4 over PT3. And so, of course, we can solve that very easily for PT4 is equal to that burner pressure ratio times PT3. And we were given that the burner pressure ratio in this case is going to be 0.94. So some losses due to friction effects and mixing and other things in the combustor. So we're going to have that times 88.919 psia, the real discharge pressure of our compressor. And that's going to leave us with a final working value of PT4 is going to be equal to 83.584. So we're losing about 5 psi 5 psi in the combustor in total pressure. So in order to figure out what's going on with the temperature and the mass flow rate, we need to go ahead and evaluate the energy balance for our combustor. So we know that basically all the energy that's released by the fuel times the efficiency of our combustion would be equal to the energy required to heat the air going through the going through the combustor, as well as the fuel that comes in. So we can write that by saying that the burner efficiency times the mass flow rate of fuel times the heating value of the fuel is going to be equal to the mass flow rate of air through the combustor times our specific heat times the change in temperature of that air going through the combustor, TT4 minus TT3, plus also the mass flow rate of the fuel times the specific heat actually of air, if you remember our approximation, times TT4, the discharge temperature. We don't have to say put in a TT3 here because that's actually already been included in our delta H value. Since we already know that TT4 is 2,480 degrees Rankine, that was given in our problem statement, really, again, we're solving for what's our mass flow rate of fuel that's necessary to accomplish these temperature changes. And so just to solve this equation, we can put in m dot f is going to be equal to the mass flow rate of air through the core times the specific heat for the average temperature of the combustor times TT4 minus TT3 over our burner efficiency times delta H minus CP times TT4. And of course we want to evaluate our properties at the average value for the combustor. And fortunately in this case we don't have to iterate because we know both TT3 and TT4. So we're just looking at the average of TT4 and TT3, which would give us a property temperature of 1789.36 degrees Rankine, and we evaluate our specific heat there at 1 atmosphere, we'll have 0.2701 BTUs per pound mass degrees Rankine. And so that's from here we can just substitute in our numbers. Say the mass flow rate of fuel is going to be equal to our mass flow rate of air, 155 pounds mass per second, times our specific heat here, 0.2701 BTUs per pound mass degrees Rankine, and times our difference in temperature, 2,480, which is TT4, minus 1095.2 degrees Rankine, which is our TT3, and it's It's going to all be divided by our burner efficiency, which was given to us as 0.92, times our heating value of the fuel, which also was given as 17,900 BTU per pound mass, and then minus our specific heat again, 0.2701 BTU per pound mass degrees Rankine, times TT4, which is 2,480 degrees Rankine. And so checking our units, of course the Rankine will cancel out, and then everything will be in terms of pounds mass, or we'll have BTU per pound mass with the numerator and denominator, and we'll be left with units of pound mass per second here. So we can say the mass flow rate of fuel will equal 3.661 pounds mass per second of fuel.